I'm Oleg Antipin, as you see on my slides, and I'm from Ruđer Bošković Institute in Croatia. And today I'm going to talk about this scaling dimensions of the fixed charge operators in the CFT, broadly working in this large framework expansion developed by Domenico and Suzanne and collaborators, of course. And the content of the summary of my talk will be like, I will start with the broad introduction to see where we are broadly in particle physics, let's say. And then I'll have a couple of examples in the time-honored U1 and ON models where I will try to set up our technical methodology of calculating things in as simple possible way as I can, before I go to the general strategy and more complicated example of the linear U1 times UM linear sigma model, where I will try to show you how we can extend the technology from the simple examples to calculate very complicated things for the conformal anomalous dimensions of the operators in this example of the UN times UM. Okay, with this, let me start. So broadly, of course, our goal is to solve quantum field theory, which is, of course, a very ambitious task. But which tools do we have at our disposal? Of course, as you all know from the quantum field theory courses at the universities, we start with the perturbation theory, in which case we have a small parameter and quantum field theory simplifies. So there are various examples known of this perturbative approach. Of course, perturbative loop expansion in the H-bar coupling through the Feynman diagrams is what we all learned from the university courses. There are a few other examples in a similar spirit. For example, in gauge series, imagine you have underlined SUN-C gauge theory, and C is the number of colors, like here you see this NC parameter. And you can take this parameter to be large and define what is so-called 1 over NC expansion, large color expansion, large number of colors. And you can show that at the leading order, you have so-called planar limit, which is to say that only planar diagrams, Feynman diagrams, survive. And planar diagrams are the diagrams shown here. You see, they kind of can be drawn on the plane, and they intersect only at the endpoints, you see, of the edges, kind of. While the non-planar diagrams, you kind of have to go outside of the plane to draw them, or just to say that, you know, the lines intersect not only at the endpoints, but actually in between. So somehow you cannot draw it on the one plane. And non-planar diagrams are suppressed, what you can show by 1 over NC factors. So they're subleading in the large number of C expansion. In similar spirit, you can imagine gauge series now to take number of matter components, which I call NF, to be very large. The prototypical example is the QCD-like gauge theory with the many number of quarks, for example, and this number will be NF. In this case, the leading order in 1 over NF expansion now will be so-called bubble diagrams, where basically bubbles are these loops of the fermions, which now dominate everything because of the multiplicity factor NF coming with every loop of the fermions, and this is a big number. So basically, to lead an order in this expansion, you just dress every gluon line with these bubbles, and you are trying to resum them, which is actually possible. And this will be the leading term in the 1 over NF expansion. And again, it's calculable, and you can work around this limit, consistently defining high order terms. But the topic of this talk will be similar in spirit to this large NC and F expansions, but will be a large charge expansion, of course. And where you will see that the topology of the Feynman diagrams, which we'll select as the organizing principle a bit later. They're shown here, but I will come back to them later in the talk, and you will see more exactly which ones survive in order and why. Okay. So the main point, the main common feature of this expansions is that we are trying to reorganize basically perturbation theory by categorizing Feynman diagrams according to the expansion we are taking. At the end, of course, we have to calculate all the Feynman diagrams. There is no magic here. But defining various limits, we're reorganizing which ones we compute first, which ones we compute later, and that's it. So basically, you see, I schematically show it like observable. We can compute it in loops, as we usually do, which is just a Taylor series in the coupling around the origin, small coupling. G is the coupling, and L is the loop counting parameter, and some polynomial where this number n is represented typically, number of colors, of labels, or charge. This would be your usual loop expansion. But now we're trying to rewrite it basically, taking a different limit where we have this large number and C and F or charge. And now we are trying to reorganize it. And what happens automatically to have a well-defined limit, you have to define so-called 't Hooft coupling, which is the product of the original coupling you had in your gauge series, say, times this large parameter n. For example, in the planar limit, it will be G squared times NC, which is G is the gauge coupling. And this parameter you are going to keep fixed. Or it can be just G squared NF in the large NF bubble diagrams limit. In the large charge expansion limit, it will be G times Q, which we have to fix. It's a different power of Q because I'm not talking about gauge series. I'll be talking mostly about the scalar field series. So the power of the coupling will be different. It will be not gauge coupling, but will be the typical quartic interaction. That's why it's G to the first power. But the philosophy is very, very similar. So this is our setup for the large charge expansion. Okay, so now it starts to be a bit technical, but I think we can pass. It's not so scary. I will try to remind you how we can define perturbative loop expansion, the standard textbook Feynman diagrams, in a semiclassical approach, which will be convenient for me to use later. So we're taking the simplest possible U1 complex scalar model, shown here, the action for this model, and we will rescale our scalar field with the square root of the coupling. And as you see from these two terms, if you plug this rescaling, there'll be overall 1 over lambda coming to the action. You see, so the kinetic term will give you 1 over lambda. And the second term will also give you 1 over lambda. There is this is quartic interaction. There is 1 lambda here. Overall, there'll be 1 over lambda. So the whole action will scale as 1 over lambda here, as you see. So your 2-point function for the scalar fields, phi and phi bar, will be given like here. And you see, since lambda we take very, very small, it can be considered as the loop counting parameter, basically, as we all know from the university courses. But also the path integral itself will be dominated, of course, by the extrema of the action. And this is what we call a semiclassical approach. We are going to evaluate this integral via saddle point approximation by expanding the action around the stationary configuration. I will call generically phi 0. In this case, we're expanding around free field theory. So our vacuum is free, phi 0 equal to 0. But later we will see this stationary configuration can be different from 0. And this is the expansion of our action, usual representation. Phi 0 is the solution of the classical equation of motion. Okay, I hope everyone is with me. And now we just make a little bit of twist to this logic and trying to come to the actually large charge expansion in the semiclassical picture. So we're talking about U1 scalar field theory. So our field phi and phi bar carry charge plus or minus 1. And so phi n and phi n bar fields carry charge plus n or minus n, as you see here. So we're going to consider 2-point function of phi n and phi n bar. And again, the fields are rescaled as before on the previous slides. So we have this path integral representation of the correlator, as you see here. And the insertion points are now phi n bar and phi n, as you see here. So the trick we're going to make is that to bring this phi n and phi n bar to the exponent. And that's what is shown here. You see now they disappeared from the bottom and went to the exponent with the logarithm factor of n went out of the logarithm. And so we have this term now, which is lambda 0 to the n, overall 1 over lambda 0 as before. And this insertions of this phi n operators as a log, as you see in the exponent. So this is what we have. And what is the importance of this rewriting? Is that, first of all, you see, as I promised to you, we now see already the appearance of the 't Hooft coupling, as I mentioned to you, which is the usual quartic coupling times n. And this will be the variable to talk about if we want to take, let's say, a large n limit. So the series not automatically organizes itself in this coupling. That's the first point. And second point, this dependence which we see in the exponent invites us to perform a path integral via saddle point expansion now around the stationary points of this effective action, which have this insertions of the phi n, log phi and phi fields to the n power. So we have to consider the stationary points of this mu effective action. And we will have as a result of this, of the working around saddle point of this effective action, we will organize our 't Hooft expansion in the coupling lambda n to all orders in this new expansion. So for example, we will be looking for the conformal dimension of the phi n operator in this U1 scalar field theory. And as you see, it's already invites us to consider it as an expansion where the coefficient functions delta k, I see here, they are function of the 't Hooft coupling, lambda n. And delta k will be the k plus 1 loop correction to the saddle point equation. Okay, any questions so far, guys? So
maybe if I can ask,
yes,
yeah.
Please.
Well, I just wanted to ask you, like, so the expansion is going to be organized with a renormalized coupling, right?
Yes, thank you, Nicola. Yes, I was a bit sloppy. Just it was a bit difficult to put all together, right? So you see, lambda 0 coupling from now on is kind of bare coupling, starting from the Lagrangian. You already see like here. This is the bare coupling, right? So we have to renormalize the coupling, of course. So all I said will be true, but of course now what we are, this coupling lambda is now a renormalized one. And all I said so far, you have to take a limit where this lambda is renormalized coupling and will be large. And renormalized coupling means just it will be coupling of some renormalized scale m in a moment.
Should matter at leading order, right, in your saddle point, right?
Yes, yes, yeah. So thank you. I kind of skipped this point. It will be a bit later, more clear, but in general, it's a very good point. Thank you, Nicola. Sometimes you will see lambda 0, sometimes you will see lambda. The point is that you will see that at leading order in this expansion, everything will be classical, typically, in this large expansion.
Yeah.
So it's a generic, yes, it's a generic problem that leading order in this large quantum number expansion is classical, right? So to the classical order, you can take a bare coupling or renormalized to be the same, basically. But once you go to genuine one loop correction, you will have to take a renormalized coupling in this technical step of renormalization. Yeah, sorry.
Thank you.
Is it clear?
Yeah.
Yes. So yes, thank you very much.
Maybe Philip also had a question. No?
Yes, please.
No, it was the same question.
Yes, exactly. So thank you very much. It's actually a very important point, and I was not very clear about that. Yes. Actually, as we go to quantum corrections to the classical physics, you will see this step more clearly. And at this moment, it's more like just to set up a little bit the big picture. Yes, but all in all, we have to now try to find the stationary configurations of this effective action. And it will no longer be, of course, not necessarily will be the origin of the fixed field space anymore. It can be some non-trivial saddle point. But in any case, we have two options basically to go about solving these classical equations of motion. Either to solve them again, let's say perturbatively, where this lambda 0 times n is small. Or we can try to exploit conformal field theory in the following sense, that we'll now consider our U1 scalar field theory in 4 minus epsilon dimension. As you all know, for epsilon being small, this model will feature Wilson-Fisher infrared fixed point. So working at that infrared fixed point, we can exploit the constraints of the conformal symmetry. And in particular, what will be important for us, we can use the operator state correspondence to make progress in solving this system. So I have a couple of slides about operator state correspondence, but you all know, of course, the main point of this is that working at the Wilson-Fisher fixed point will basically map our theory to the cylinder, from the plane RD to the cylinder, and the point is that the eigenvalues of the dilatation charge, which are our conformal dimensions delta phi n I mentioned about, which we are trying to compute, will be mapped to the energy spectrum of the cylinder, of the energy of the which are the eigenvalues of the Hamiltonian on the cylinder. So this is the philosophical step we are going to take. And more technically, what we are going to compute, again, we are working with the 2-point function of the phi n and phi n bar scalar fields now in the cylinder, and they take this form in the CFT. Again, delta phi n is the scalar dimension of the phi n. As I already said, we are going to compute the energies, and delta, which are conformal dimensions, relate to the energies of this expression. An important point also is that we will be looking for the scaling dimension of the operator. We'll be looking for the operator with the smallest scaling dimension. So we will be computing the ground state energies, the smallest energies through this equation, as you see. And technically, how we're going to do that, we are going to compute expectation value of the evolution operator e to the minus ht. H is just the Hamiltonian on the cylinder of our U1 scalar field theory. And this expectation value will be in the arbitrary state I call psi n with fixed charge n. This state can be arbitrary because it can be arbitrary in the following sense. As long as there is overlap of this state with the ground state, this is enough, because taking the limit t going to infinity, you see this matrix element will be saturated by the ground state energy because of this exponential factor. And so all we need to make sure just there is an overlap of this state with the ground state energy. So otherwise the state is arbitrary and we can choose it as we want. And in particular, the choice I'm going to make for this state psi n is as follows. So it will be a state psi in which the radial coordinate for our complex scalar field will be fixed to some constant value f, as you see here, f. So it will be like kind of constrained path integral where the radial mode is constrained to be f, constant value. And all we have to do is now kind of evaluate the time evolution now in time, basically, this tau variable, as you see. I am using polar coordinates for my complex scalar field, as you see here, and chi is the phase of the field. So after performing a few simple technical details, you can basically take our previous effective action I drew a couple of slides ago, plug this field's representations in polar coordinates. You will find this first 4 terms, just the usual quartic interaction, kinetic terms for the modulus. Now there'll be new term, mass term for the rho. This is just comes from the going to the curved manifold cylinder. This is because we are coupling our theory to the Ricci scalar. And also there'll be new term, this red term, which is just fixes the charge of the initial and final state psi n to be n. You see, so this is the physical interpretation of this effective action. So now this is our effective, and omega, of course, is the solid angle in d minus epsilon dimension. So we are now working at the leading order, which means we have to solve this classical equation of motion, as I mentioned to you, finding this phi 0 stationary point. This stationary point will be parameterized as follows. As I already mentioned, the radial dependence will be constant, this f, and the phase will be parameterized with this factor mu, chemical potential, which we fix by fixing the Noether charge of the system to be n. Basically, you see the charge density, charge over volume, will be equal to this usual expression, mu times f. F is basically the wave of the complex scalar field, if you want. So I forgot to mention that we are looking for the solution with the minimal energy, which is spatially homogeneous in space. That's why there is no dependence of these factors rho on space-time. If you'll be considering especially non-homogeneous solutions, this can be different. But then you're considering excited energy states. So it's very important we're considering ground state energies here. So our classical equation of motion is shown here. Our Noether charge is fixed to be n. Constant factors mu and phi will be fixed through the equations of motion. And we have to evaluate now our effective action on this classical solution. And what we are going to compute at leading order in this expansion is this delta minus 1 term in the delta phi n expansion. And this is the classical contribution in the large charge limit. So let's see what happens more technically. I skip some steps, guys, which they're quite trivial, really. You have to solve these equations of motion, plug them back to the effective action here, and this is your answer basically. You'll find energy, and energy is related to the conformal dimension. As I already mentioned, through this equation, energy is equal to the delta and r. So after all the smoke clears, you'll find the leading correction to the ground state energy or leading correction to the dimension of the phi n operator, this delta minus 1, and is given by this function here. Important to notice is that this is the function of only 't-Hooft coupling, lambda n, as you see, as it should be, as we motivated by the general considerations before. Also, I put lambda star here, as you see, to remind you that we are really working at the fixed point, at the Wilson-Fisher infrared fixed point. So you can now expand this function in various limits when this 't-Hooft coupling lambda times n is smaller than 4 pi or less or bigger than 4 pi, to have a sense of the usual small charge versus large charge expansion. In the small charge case, you will recover the perturbative expansion around the uncharged vacuum, basically, as we discussed before. Remember, when charge is small, you're basically very, very close to the origin of field space. And basically, you're starting to recover the usual perturbative expansion around the uncharged vacuum. And that's not a surprise. In fact, you will see in a moment, it's really what happens. In the large charge limit, is quite different. So what is the interpretation? So as I said, in the small charge limit, we are just recovering the standard perturbative expansion around the uncharged vacuum, which can be seen to be in one-to-one correspondence with the following Feynman diagrams, which are shown pictorially here for this operator phi n. So you see, this is the one-to-one correspondence with the terms which appear in the classical energy. And for the large charge, large lambda star times n, the system will be in the superfluid phase. Clearly, you'll be very, very far away from the uncharged vacuum. So theory is charged, and strongly charged. So there is no long interpretation in terms of the standard perturbative expansion around the vacuum. System will be in the superfluid phase, and that's the expansion in this limit. And this is the large charge expansion, which originally was found by Domenico, Suzanne, and collaborators, as I mentioned, Simeon and Masataka. So, any questions about this point, guys? I hope you're still with me.
Maybe if I can ask again.
Yes, sure, Nicole, please.
Like, can you show me again, like the function that you get for this leading, the full one? Yes, this thing here. So this one is basically just the action at the saddle that you found, right?
Exactly. It's really just that. You just really evaluate this. See this action. Right. You plug the solution of the classical equation of motions here, and this is what it is really.
Of course, it has no singularity on positive x, right?
Yes, I think it's also consistent with your resurgent results in your paper, right? If I remember correctly.
Well, yeah, I just wondered because these of course is a convergence series.
Yes,
you have a function. You have a function here, so that's.
I mean, the small charge expansion here for the small, small. I mean, this one is totally convergent. This we checked. And this one, I don't know. Probably it's also convergent. But I think yes, it's in both sides. It converges expansion basically. Yes.
I mean, it doesn't need to be honest. It can also be asymptotic at the large charge end. It's just that if you have the full thing in this form, I mean, I won't see how that would work. But okay, I mean, but this you just get it from the profile, the profile of your solution, right? That you
yes. Of course, to be clear, once you compute all orders, Nicola, for the conformal dimension, you see here. Once you compute all order, it will be definitely asymptotic expansion.
Oh, yeah, that is for sure.
This is for sure in both perturbative regime and large charge. And we just compute the leading term, right, which is classical result.
Yeah.
And in that case, just like in large NF, remember when you sum bubble diagrams, you find a convergent series in perturbative setting. That's for sure. In the large charge, I didn't check to be honest, but I think it's also convergent. The classical result only.
Yeah, because there's also this one, right, is a double expansion. I mean, you're expanding in one of the lambda, and then each order is a full function of your tooth cup.
Exactly. It's just
Okay. Yeah.
It's just leading in lambda, but all order in the lambda n. It's all order. Exactly. In fact, this is the order result. This function here. In fact, you see, I showed you first few terms, but we know all order result. In fact, I'll mention this in a moment. Thank you for helping this, but it's good that you mentioned this. That's the advantage of this result. Of course, it's a classical result, but it's all order result, which means we're resumming infinite number of Feynman diagrams. But leading diagrams in the charge, of course, not all the diagrams, but just leading ones in the charge, but all order, which means the diagrams of this kind of topology. Right.
Okay, thank you.
So very similar to the large in many aspects. In fact, just to mention,
Oleg, maybe Philip also has a question.
Yes, please.
In finding the saddle points, you're looking for sort of real saddle points, but often in the saddle point expansion, there can be complex saddle points that might contribute. Is this something that you look for, or is it just that in this problem, they don't contribute or they're subleading?
In the way it's set up, particularly here, I think it depends a lot on this arbitrariness of the state psi n, as I mentioned to you. I think there's some freedom how you choose the state, and
well, even within your choice of psi n, you could have simply complexified your field space. So you could say the field phi, instead of being in two real scalars, rho and chi, you could allow rho and chi to effectively be complex.
This we didn't explore, to be honest. This we didn't. So basically, you want to,
if I may add something. So
yes,
I think so. You are complexifying the Gaussian field, right? But you're not complexifying the scalar field. And this, as you said, comes from so there are three saddle points of this kind: two with complex rho and one with real rho. And the reason why you pick the one with real rho is because you chose the state which you start with a real value of rho, so that you never have to cross the other two saddle points. And there might be inhomogeneous saddle points which are complex, and those we were never explored. But homogeneous saddle point compatible with the boundary condition, there is only this one, I think.
Yes, I think yes, compatible. Yes, exactly. As I mentioned, yes, this state you choose for the Exactly. Thank you, Gabriele. Yes. Okay.
May I ask a
Yes.
quick question? In the classical contribution, do you have a branch point at the special value of x equal to square root of 3, or is that just an apparent branch point in this complicated cubic root?
You're talking about this one?
Yes.
Actually, it's a good point. I somehow, to be honest, never thought about this. To be honest, what playing with this form, it's actually it's a good question. To be honest, I know when you play with this function, it looks very complicated, but actually it's a bit magical function, you know. It simplifies a lot and many things cancel once you actually write in different form, you know. So it looks like a singularity, yes, but I have no more comments to say actually about what happens at the x equal to -3.
I mean, for instance, a simple question may be if you take a small value of x, I see the expansion is real.
Yes.
Does it mean that this complicated expression is always real for positive x? This would be not surprising because actually historically complex numbers were discovered precisely in this way. There were cubic equations with real roots and intermediate complex numbers in the, how do you say, maybe Tartalga solution, I don't remember.
Yes.
No?
Well, yeah. Well, somehow you see on the physical grounds, we're looking, our x is of course lambda times n, right? So we're kind of looking for the positive x, right, on the physical grounds.
Yes, yes.
Of course, this question might be related to what Nicola was asking. I think in the recent paper on the resurgent structure of this large charge expansion, if I remember correctly, the convergence properties of this expansion will be different depending you have a positive or negative charge, right, Nicola, if I remember correctly?
Yeah, I mean, you have like a small charge which is convergent. It's at large n, so I don't know how it maps.
Yes, yes, it's a large n, but also there we find that like the singularity point happens at the negative charge, if I remember correctly.
Yeah, but for us, like it's even harder in the sense that, I mean, we don't have a full function, right? We have an explicit function in terms of theta function, and we can just only expand. We cannot really see singularities. Like in this case, we wouldn't see like that a square root of 3 something, there's a branch point, or maybe not. So that's the thing, because this is so clear that, I mean, but probably there shouldn't be any problem before a square root of 3. Otherwise.
So this is only apparently complex for us.
I think so.
Less than.
Yes, I think so.
Okay, thank you.
Yeah, it seems to be real. Yes. Okay, thank you for your questions, guys. Thank you. It's very important. Okay, after this physical interpretation I gave you for the classical solution, we now move a bit to the one-loop correction. And of course, as usual, you now have to expand your fields around the classical equation of motion, introduced by these fluctuations, which I call R and pi, and find the action to the quadratic order in fluctuations. And then here I'll be very brief. The setup is very standard, of course, and you can show that the one-loop correction to the energies, which I now call delta 0, and LO, next leading order term in the large charge expansion, will be determined by the fluctuation determinant around the classical trajectory. And I didn't show it here in more details, just to speed up a bit, because I'm still reviewing the known results in the literature. So you can show that this energy, or component dimension delta 0, and LO energy, can be written as in this form, where this NL is the multiplicity of the Laplacian on the d-1 dimensional sphere. And omega I will be the dispersion relations of the fluctuations, which you'll see in a moment. And each fluctuation will be counted with its multiplicity GI. In our case of the U1 complex model, of course, fluctuation spectrum is very simple. You'll basically find the inverse propagators from this quadratic action for two scalars R and pi. And you'll find you'll have one relativistic Gaussian boson, so-called conformal mode, type 1, massless Gaussian boson of the broken U1 global symmetry, and one massive state with mass square root 6 mu squared minus 2m squared. Their dispersion relations are very easy to find. They're shown here. And basically our formula from the previous slide, our formula in this case boils down to this expression where you just have to sum over these two states. But now comes the important point about normalization, which already Nicola mentioned a few slides before. Now we're really at the first genuine quantum level. And this sum will be formally divergent, this sum over L. And it will require regularization and renormalization. I don't want to review here how it's done. There are various ways to do it. Let me just state without the proof that the NLO result, again, it's quite, now the expression will be quite long to write it in here on the slides, but taking the expansions again in the large and small charge limit, again, in the small charge limit, you'll find that now the next to leading order corrections to a perturbative expansion around uncharged vacuum, not surprisingly. And in large charge limit, you will find the next NLO correction to the superfluid effective field theory Lagrangian I put it before. And this was found, of course, with these coefficients alpha and beta in the paper by Ricardo, Gabriele, and others, which was just really borrowed from there. So all the details can be seen in that paper, and I state them without proof here. Just wanted to mention few generalizations of these results to d dimensions. So far we talked about, if you remember, Wilson-Fisher fixed point in 4 minus epsilon dimension. Epsilon is small, but if you go away from the being close to 4 dimensions, this result generalize as follows. In the small charge limit, kind of perturbative limit, we will be always finding kind of Taylor power series in this Hopf expansion I mentioned to you. But in the large charge limit in generic dimensions, the general form will be written of the expansion will be written in this form. And of course, originally, this was found by Domenico, Suzanne, and collaborators was in 2015, the original starting paper of this large charge expansion, where in 3 dimensions, they found leading terms in this expansion, doing completely different approach, effective field theory approach, not semiclassical approach like here. So this is the first comment I wanted to make about the EFT approach to this result in the superfluid phase. And the second important point, which was I borrowed from the paper of Gabriele, but also which is very easy to see here, looking at the classical term, which is the top line given by this alpha I coefficients, you see that the even and odd dimensions are very different. Since if you have an odd dimension, the top line will never have a contribution scaling as Q0 power, never. You see Q0. Physically, it means that in odd space-time dimensions, the one loop correction, which is this second line, cannot be normalized by any local counter term. And therefore, this quantum correction will be finite and calculable. And in particular, again, it was, for example, in 3 dimensions, this beta 0 coefficient is given by this number. Also, beta 1 can be found, but I don't write it here. But these numbers are finite and calculable in any space-time dimension, which is odd. Okay, so this is the first comment about.
Sorry.
Yes.
I have a question.
Yes, please.
Can this beta 0 be computed in the epsilon expansion? Has anyone done that?
So please say it again. Sorry.
No, has this beta 0 computed in the epsilon expansion? Has anyone done that?
Let me think for a second. I think yes. For example, in the U1 and ON model, we do work in epsilon expansion, right? So, and we did compute Ricardo, and we did it in the ON model. Ricardo did it in the U1 model. This beta 0 is computed in the epsilon expansion. Yes. If I understood you correctly, it can be extracted from this delta 0 term, right? Or maybe I missed something. We do have this NLO term. You're talking about
I think so, but wouldn't it be too high of an order? Don't you have to go to very high order to do that? I'm trying to remember.
Yes, a good question. I think, to my understanding, is that this second line is just really the kind of NLO contribution I was talking about, given by this delta zero. Remember? This
I get it. No, I was just wondering.
And since we really computed this in epsilon expansion, we really did. And there is no problem to expand it to the small and large charge limit. So in the large charge limit, I think you do, at least numerically, can find this coefficient beta zero, I think, with no problem.
Yeah. No, I was just wondering if how much higher order you have to go in order to do that. But it's okay. Thank you. Yeah.
Yes, right. I cannot be maybe more sharp on this point, but I think, yes, this is basically, this term is somehow in these results I showed above, basically, for the U1 model and the ON model. If you want to generalize, I think it's there. I don't have the expression for now to show you, but I think, yeah, they're computed basically, or can be computed, at least numerically, for sure. I think in the epsilon expansion. Yes. Right, so the generalization I mentioned to you, obvious one, of course, is the ON model. This is, of course, just a trivial step from the U1 model, which is O2, basically I did so far. Now we generalize to the n component fields, phi I, n component scalar fields. Again, G0 is the Bayer coupling. But okay, I'll just highlight a few differences with the O2 model without giving too many details. Of course, the rank of the group is changes now, being n over 2 or n minus 1 over 2 for the ON model. So when n is equal to 2, which is U1 model I considered so far, we have just one charge, obviously, which I was talking about so far, n. But now in the case of ON model, you can fix at most n over 2 or n minus over 2 charges, depending on even or odd n. And you introduce complex field variables for all these fields, n over 2 fields, and you can decide how many charges you want to fix in principle, up to n over 2 at most, or n minus 1 over 2 charges you can fix. So this is so you have many charges to fix, but otherwise, again, you're looking for classical solution of the equation of motion. There are now several waves and several, of course, phases, But important point, what you can show is that still, even in the ON model, even though there are multiple charges, there is only one chemical potential, mu. And moreover, using the ON symmetry, you can show that you can rotate the ground state in such a way that basically the sum of the charges, which I defined here, Qi, which you introduce, no matter how many of them you introduce, 1 or n over 2 at most, they basically act as a single charge. So the results will be very, very similar to U1 model I was describing so far. At least at the classical levels, they're very, very similar. I will show a few results in the moment. Yes. What happens with the ON results to the NLO and the classical order. But before I do that, another important, another important aspect of the calculation, which I didn't talk about so far.
Oleg, can I ask you a quick question?
Yes.
When you say that the only thing that matters is the sum, it's because you are assuming homogeneity, right?
Yes. Sorry. Thank you, Domenico. Yes, we're still looking for the homogeneous ground state. Yes. Okay. Yes. Thank you very much. So it's here. It's still spatially homogeneous solution. Yeah. Thank you. Thank you. Yes. Right. So another aspect I didn't mention so far, we've been computing this classical energy and first quantum correction to the energies on the cylinder, but I never mentioned to you so far which operator corresponds to these conformal dimensions. And it's actually not very easy to figure out, of course. So basically in the perturbative regime, at least, when coupling is small, you should imagine that, we should consider operators without derivatives, just because the derivatives will increase classical scalar dimension by 1. And in the small charge, in the perturbative regime, this is the large change in the dimensions. So those ones with the derivatives should be higher order, higher scalar dimension operators. And since we are looking for the smallest dimension operator, those are not the ones we expect to find. So it's quite natural to understand that what we found is actually the operators without derivatives, actually the fully symmetric ON space, which is composed of the singlets and M index traceless symmetric tensors. So these are the operators of this form, basically, where T is just the traceless symmetric tensors with charge. Well, here I called M, but it can be N, of course, in the previous slides, and classical dimension M plus 2P. So basically, the results I found so far in this ON model corresponds to the operators given by this Young tableau with one row, basically fully symmetric tensors. You can write them in terms of fields, but I think it's all well known, of course, for you guys to how to write a traceless symmetric tensor in the ON model. So the charge Q or N, I was calling before, corresponds how many boxes you have basically in this row. So these are the operators really underlying the conformal, for which I computed the conformal dimensions in the previous discussion. So now that we identified the operators which correspond to our computation, we can compare in principle with the literature, where for the traceless symmetric tensors, the results are known in the standard perturbation theory around the uncharged vacuum, just standard Feynman diagrams calculation. And in particular, results are known up to 4 or 5 loops sometimes, but only for operators with small number of Q, basically 2 index, 3 index, 4 index symmetric tensors, which means 1, 2, 3, 4 boxes. Nobody goes to the arbitrary Q. But in this approach of the large charge, as you see, we automatically work with arbitrary Q. In fact, our Q should be even large because we have a large charge. So in this approach of computing Feynman diagrams to all orders, we automatically reassign it to all orders and also reassign it for any Q automatically. And in fact, just to show you that our classical energy delta -1 and delta 0, first quantum correction, if you rewrite back your large charge expansion in terms of ordinary perturbation theory, basically at every loop order, you'll be finding the first 2 leading terms in the Q. They're shown here with red. So this, for example, first term is the one loop result. You see it's epsilon to the first power. These 2 red terms, it's Q and Q squared. So Q squared terms is the classical result. You see it's a leading in Q. And the linear term, which is Q, this is the Goldstone, this is the delta 0 result, which is the functional determinant I was showing you before. And since we sum 2 all orders, we can go higher orders. For example, at the 2 loop order, again, we found Q squared and Q cube results, which can be compared to the standard perturbative result. But we are missing the linear term in Q now, because this would require NLO computation in the large charge expansion. And this, of course, we haven't done. And so on and so forth. So if you continue to higher orders, you'll be missing more and more terms in the standard expansion. But at any order in the standard perturbative expansion, you will have 2 leading terms in charge, always, to all order, because we have a resummed result. So compared to the standard perturbative result, you can do infinite checks if you want. If in future you compute these results to higher loop order. But this infinite order check can be done only for the first few terms with the highest power of Q at every loop order. So I don't know if I explained clearly, but are there any questions about this?
Do you have like, do you know if these correspond to some particular class of diagrams? I mean, to which one?
Well, I kind of schematically showed in the, if you remember, let's say classical results. I mean, this would be the diagrams kind of.
This is for delta -1, right?
This is for the classical one, right? For the Goldstone, I probably can figure it out. It's not very hard, of course, but I didn't have it here. But similar logic, I mean.
But it should be. I mean, there should be a class,
right?
Class which is iterated like this.
Exactly, they just iterate to higher loop orders. You see, there's an interplay between number of external legs, which fixes the charge, if you want, and external legs, and number of loops. You see, so there's interplay between the loop expansion and the charge expansion, as I mentioned. So you can rewrite one in terms of the other, and that's why you can kind of rewrite back all you found here in this large charge limit back to the ordinary perturbation theory, right? For the Goldstones, the results will have a 1 less power in n. You see, Nicola?
Yeah, because it's subleading.
Yes, you see, it's like if you take this and compare with the Goldstone, it has basically 1 power of n less. You see, classical one was lambda n squared. Here it will be lambda n, the first term for the Goldstone. You see, and this is the general logic. That's why these red terms I showed here. Sorry, guys. These red terms I showed here. The highest one at every loop order is the classical result, and the next one is the NLO result. And so these are the red terms you see here. For example, q to the 4 will be the classical one, q to the cube will be the next reading order. And you can go to any loop order, and it will be always like that. But you'll be missing more and more terms, of course, of the lower q order, you see?
Yeah.
One question, what is the origin of set of 3, Riemann set of 3?
Well, I mean, I think this is just a standard, you know, kind of zeta numbers which emerge in the perturbative preparation of Feynman diagrams. I don't have much more to say, but right, they're typical there. Yeah. These results are just borrowed from the literature. You see, we didn't compute these results. They're just, you know, standard, you know, zeta functions which emerge in the perturbative preparation of Feynman diagrams. So I really don't have more comments on that. Maybe somebody will have some comments.
And they are sort of related also with the class of diagram that you actually have. I mean, some zetas can appear in some classes and some zetas cannot in others. So I mean, there still should be a relation. It's just maybe not apparent.
Yes. 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 Okay. So Domenico, how much time I have?
5 minutes.
Okay. Yeah, I was really slow, guys.
10 is fine.
Yes. So sorry, guys, I was really slow, but I think it was very nice.
That's okay. We had a lot of questions. Go on. Don't worry.
Yes. So I'll raise questions and I'll be really brief from now on, even though the second part of my talk is really about kind of original work we did on the subject, while so far I was mostly reviewing the results by Gabriele, Ricardo, collaborators, of course. But I think it was very nice maybe to have this few things discussed here as a first talk on this seminar and lectures. Anyway, the few important questions I view as we go on is that in the perturbative regime, we identified our operator with the traceless symmetric tensor. But in the superfluid phase, where a system is strongly coupled, it's in principle, other operators can become important. And in fact, level crossing can happen where other operators can have a lower dimension than the ones I mentioned for the traceless symmetric tensor. So in principle, it's not clear to me that in the superfluid phase, we're still talking about these operators. And I'm not even sure it's a well-defined question. Who are the operators? What are the representations of the operators underlying the result in the superfluid phase? So this is just, maybe somebody has a comment, but this is just to be clear that all the identifications I made for the operator structure in principle should be taken only in the perturbative regime of the small 't-Hooft coupling. And the second important question I will talking about for the rest of the talk, which I will not talk mostly at all probably, but just to give you a hint what I should be talking about, is actually for the general global symmetry group. How would you identify the given charge configuration and the associated operators? So basically extending this identification for the traceless symmetric tensors to other global symmetry groups. And that's what we've done in our latest paper. And I'll be really, really brief. And basically you see that the outline of the strategy is that we'll be, of course, assuming that only the lowest line operator corresponding to a given charge will be still saturated in our computation. So basically we don't have to consider operators with derivatives, basically. This is, I think, the standard kind of safe assumption to make. In perturbative regime, again, I emphasize that we are working in the perturbative regime where we expect level crossing not to happen. And second point, you see, it's natural in the semiclassical computation, which I've done so far, to fix the charge configuration. And it's not a priori obvious how it corresponds to the irreducible representation of the underlying operator. Somehow this is hidden in the fact that only lowest line state is projected out. And this is was a bit kind of overlooked in the literature, I think, and we made some progress in this direction. And basically the logic is very simple. For a given global symmetry, we will basically start to write all possible charge configurations you can write and compute semiclassically the energies for all of them. And then if you're lucky and you find different results for different charge configurations for the energies, and you assume that you are talking about operators with the minimal classical scaling dimension I mentioned, you have a chance basically to disentangle which charge configuration corresponds to which irreducible representation. And this strategy we kind of carried out in the UN times UM linear sigma model. Of course, I don't have basically no time to go over this, maybe 5 more minutes, right? Domenico, can I have 5 more minutes? Sorry.
Go.
Yeah, sorry. Yeah, so basically 5 more minutes, guys. And Domenico, please stop me if I go really long. So basically, to complicate our starting point, we have to have a more complex model, which we took to be a linear sigma model in 4 minus epsilon dimensions, again, shown here. And basically, you see the U0 couplings breaks the ON symmetry, which we had before, to the SUN times SUN subgroup. It's this coupling, while this coupling is basically ON coupling written in terms of this H matrix fields. I didn't show definition here, sorry for that, but it's basically the rewriting of our N component scalar field in terms of the matrix. So this coupling is really ON coupling V. You can basically start, so you always have an ON limit if you put coupling U to 0, and that's why this model is very nice. So there were several aspects in this model which we liked a lot. For example, at one loop in 4 minus epsilon, you will find that if you put n equal to m, let me simplify the things here, the one loop perturbative infrared fixed points for n bigger than square root 3 from these expressions, they become complex. So differently from the Wilson-Fisher fixed point in the ON model we talked so far, here your fixed points will be complex already at one loop for n bigger than square root 3, which basically for any n, as you see, for very small n. So this is kind of a bit of technical novelty. We are going to extend our semiclassical computation to the complex CFT, which are non-unitary. Everything will be working fine, but this is kind of first nuisance which will be different in this model. And the second important difference will be that now you can really analyze the role of the charge configurations, because in this model, you can write, depending on the numbers, quantum numbers here, you can have many possibilities for the charge configuration, compared to the ON model, where you had basically only single charge. Here it will be very, very different. And basically you can analyze very two parameter family of the charge configurations, which is shown here. Basically your charge has to be traceless matrix. You can show this. And this is the choice we are making, kind of the most general choice for this charge matrix. And corresponding to these charge configurations, we are trying to basically identify which are, in the perturbative regime, which are the operators and with which irreducible representations correspond to a given charge configuration. So this is our kind of motivation, so which is shown here. And I really have very, very briefly just to talk about these guys, and maybe you can look at the slides. And basically, on very general considerations and general grounds, you can understand that you're looking for operators which are without derivatives. So they are built of the H and H dagger fields. And since H and H dagger, they're kind of bifundamental fields of this SUN times SUN global symmetry. It's kind of fundamental left, anti-fundamental right. That's how they transform under the global symmetry. You see basically that if you start to take tensor products of this H and H dagger fields, you basically will have 1 plus adjoint if you take fundamental times anti-fundamental representations. And so singlet will always kind of increase anomalous dimension. So since we're looking for the operator with the minimal classical dimension, you basically can drop out the singlet components. And what survives here is there's basically a joint component, which should be the representation corresponding to the homogeneous charge configuration. So the operator we are looking for should correspond to the irreducible representation given by gamma L, gamma right of this global symmetry group, where basically these factors gamma L, gamma right, they appear in the tensor product of adjoints, which you take D over 2 times, where D is just how many fields you have. Basically, what is the classical dimension of the operator? As you increase classical dimension, you have to take more and more products of adjoints, and inside this product of adjoint, you should be looking for your operator. Basically, it's always there. And I don't have time to talk more about this because it's really impossible now in the last 1 minute. Just to show you that basically you start to vary, N and M of the global symmetry group, SU3 cross SU3, SU4 cross SU4, and so on and so forth. Start to increase number of classical dimension 4, 6, 8, so forth, which means how many fields of H and H dagger you have in your operator. And you start to write all possible mass matrices, or charge matrices, charge configurations you can write. And by doing this identification I mentioned so far, you can always kind of set up a map which, some kind of identification between chart configuration and the possible representations it can correspond to. And what typically happens, there is one operator which you can assign automatically to the chart configuration. This is so-called highest weight representation, which is unique. When you take the tensor product of the adjoint operators, tensor product, there'll be always highest weight representation in the tensor product, and this is the unique one. And you can always find the unique charge configuration corresponding to that one. And then the others can be several of them. And so to disentangle the others, you have to kind of compute semiclassical calculation for the energies and hope that you will get a different result. And then if you do, you kind of can uniquely say which one is which. So for example, for this case, n equal to m equal to 3 and dimension operator is 4, you can show that there are 2 charge matrices. These are the possibilities for the representations you can assign. So this matrix corresponds to 27, 27, which is in the tensor product of the 2 adjoints, as I mentioned, this one. But the second chart configuration, in principle, can be also 27, 27. So there is a degeneracy in principle, or it can be 10, 10 bar. And really, without group theory, you cannot go further. Sorry, without semiclassical calculation, you cannot go further. But then you start to really compute these energies. I show them here. And you find, for example, in this case, they are different. And this is enough for you to say that, really, this second configuration corresponds to 10, 10 bar and not 27, 27. And that's the logic kind of you're doing. And you can really proceed to very complicated cases. For example, you see, now you have SU4 plus SU4 global symmetry. Again, dimensional operator is 4. You can build 3 charge matrices. These are the possibilities you find from the group theory alone for the assignment. Always there is a highest weight, which is unique. And the other ones, in principle, you don't know which irreps they correspond to. But by computing their energies without semiclassical method, you can uniquely disentangle which one is which. And so on and so forth. So for example, you see here it's really complicated one. You have an operator with dimension 8, basically 4 H fields and 4 H dagger fields in the trace of this, as you write this operator in terms of the H and H dagger fields. And your global symmetry is SU4 plus SU4. You can build 7 mass matrices, charge matrices, here, diagonal. You can show, and you see here, you can really disentangle, again, uniquely all 7 of them, which is highly non-trivial representations and highly non-trivial work to be done. So with this, I really apologize to going over the time, and I will not read the conclusions. You can read them from the slide. And I really thank you guys for listening and be patient with me. And here I conclude. So thank you very much. Thank you.
Thank you very much for your talk, Oleg.
Yeah, thank you.
And if there are questions, go for it. Okay, maybe I wanted to make just a little observation. Your computation also in the UN cross UN here, this is always you assuming homogeneity.
Yes.
Or am I wrong? Okay.
Yes, yes.
Because then the observation is that generically you would expect to find other representation. Once you give up homogeneity, you expect to find all the other possible representations.
In fact,
in UN.
If you remember, you have done this for the large charge regime in the O4 model, right?
For example, yes.
You already did. In fact, I think if you now repeat this exercise for the inhomogeneous solutions, but let's say in the perturbative regime, what you expect to find, of course, kind of Young diagram with the columns, basically, right. Which means you start to put derivatives inside the operators, which means you can kind of anti-symmetrize some indices in principle. So those should be the underlying operators corresponding to the inhomogeneous operators, my expectation.
But this you have not done yet.
This is not done, but I think this would be a very nice project in principle. And yes, so this one, which is completely symmetric, corresponds to the homogeneous state. But the others will clearly have basically boxes in the columns, which corresponds to the anti-symmetrization, which requires to introduce derivatives in the operator, as we discussed, which is, I think, is very nice, kind of intact with the logic we have here.
Okay. Thank you.
Yes, yes. So the same, of course, in the SUN cross UM model, but this will be, of course, very, very difficult.
Of course.
But technically, not conceptually, I think. Conceptually, I think it's clear. Yeah.
If are there other questions?
So maybe just a clarification. So basically, you're saying that, like, for each primary in a given representation under your SUN times SUN, there is an homogeneous ground state charge accordingly, yes. which will dominate. Is going to be the dominant one, which will dominate this expansion. Right?
Yeah, precisely. That's what we find in the examples we studied, which was quite a few. Yes, exactly. Yes.
There's never going to be like a weird case in which you have like two saddle competing, right? Or you might. I mean, it's just, I don't know what.
Yeah, I mean,
this is the question. Sorry, this is the reason why we're doing it within perturbation theory. If
yes,
you go
exactly.
to the non-perturbative regime, yes. Then you have a level crossing.
Yes, exactly. I was
sorry. That's just, it's extremely important that you believe that you are close to a regime where level crossing is not happening. The moment the level crossing happens, all the bets are off.
Yeah.
That's why I think it's an important question in general, guys, for the audience and for us to understand that what happens in the superfluid phase with the underlying,
Your classification in terms of just representation in which they sit, that should be valid also in the superfluid phase, right? I mean,
that's actually the question, Nicole, you see?
With it's not going to be phi n or whatever, but it's going to be an operator in that representation.
Well, you see, in principle, the superfluid phase is the phase with the large Hooft coupling, right?
Yeah.
So just like on general grounds, in the strongly coupled regime, you can have a large anomalous dimensions, large corrections to the dimension of the operators, right?
Yeah.
So a priori, it's really difficult to say which one corresponds to the.
But if you have no reason to think, right, that you might think that there's going to be level crossing, right, once you go to strong coupling, but if you don't have any specific reason to think that might interfere with your symmetry, then there should still be like a one-to-one map, right, in the two phases, at least representation-wise.
Yes.
Yeah. You're talking about for the symmetric representation? Or?
Yeah, meaning you might not know which operator, if the operator that you're looking at in the superfluid phase is the one that you call the phi n in the perturbative part, you might not know that, but you might know that, it's still going to be that our operator with that representation, right? You can still classify it with your SUN times SUN.
Yeah, but I'm not sure you can.
I'm not sure about that, really. Really not sure. Yeah.
Okay.
I don't think you can do that. At least there's no obvious way to extract that, unless it is a very trivial theory. Maybe with U1 you can do that. But if you have a theory with non-abelian theory, I can imagine very complicated operators. We have already seen it, yeah, exactly. But I mean, we have even seen it even in perturbation theory that, you know, the operators in the joint of flavor can have anomalous dimensions which are smaller than the anomalous dimension that basically the bilinear operator in the singlet. So I mean, you really need to solve for the theory. But in non-perturbative theory, that doesn't even make sense anymore to, in principle, consider these as operators, because you have all the operators have exactly the same charge contributes equally much. So at least I cannot see how you can do that.
Yeah,
there might be some special cases where you can do it, but not in general. That's my, but I think it's natural. I mean, even the splitting between primary and non-primary operators, they might even all lead to the same charge too.
Yeah, I mean, what you can level cross, right, are other primaries, right? I mean, there might be two primaries that do that, but
you already have seen now, Nicola, that in the UN cross UM, we have many representations that even in perturbation theory are hard to disentangle.
Yeah.
The point is that, as was actually discovered by Chen and also in our work, and you see that there are so many, it's in the plot that in the slide. The point is that the charge is related to the weight of the representations rather than the specific representation. So it's not one-to-one, even in perturbation theory.
Right.
It's it's a hurry. I mean, in other words, there is more degeneracy, more operators that contribute to the same charge configuration already in perturbation theory.
It's here, guys, you see, yeah. So this result here is really group theoretical, all you can do, to my understanding, you see. So beyond this point, you cannot really disentangle more. And you really have to do the semiclassical computation we did to really say, you know, they have different energies, which means different.
So for our colleagues, like, you know, the Yan and team, right? So they would do the computation for the specific operators. Then this computation is helpful because you can check the anomalous dimensions for those particular operators in perturbation theory. But I would say in the non-perturbative regime, you're not able to disentangle which is which. In fact, you just compute an anomalous dimension of some operator with that charge, but that's not one operator.
You know, yeah.
Of course, maybe just to mention, guys, that we checked for the few cases shown here with perturbation theory, and we really have agreement with the perturbative regime. That's why we had confidence with this setup. But of course, many results we found, they don't exist in literature because these are very exotic operators. And in principle, provides a lot of new results just per se. But for the few ones really exist, and we checked and we find agreement. Very nice.
Well, for sure, you know, right, that non-homogeneous ground state should not provide you with these operators, right? Because these are all
non-homogeneous.
Yeah. I mean, there should be like a really separate issue, right?
Yeah. I mean, I think, as I said, I mean, in the ON model, I think this is the clearest way to think about this. As I mentioned, you start to build columns in this Young diagram, right?
Yeah.
This is what really corresponds to the homogeneity. So if you want, you start to put derivatives on the fields. So this probably is the kind of clear way to see it in the ON model. Something similar happens, of course, in the UN times UM. You start to kind of have anti-Semitization on some.
Right, you can obtain it in principle also from there. Yeah, okay.
I think that's the kind of intuitive way to think about non-homogeneous charge configuration solutions.
I mean, it makes sense that the higher derivatives, what we call non-primary derivative operators are associated to inhomogeneous ground states, because that's the only way you explore derivatives. That's fine.
Those aren't non-primary, those are primary.
Still primary, those with derivatives?
Those are primary, yeah.
Okay, okay. So what, sorry, remind me, what are the non-primary operators?
I mean, the non-primaries are just the non-primary. I mean, the non-primaries all have derivatives, but the converse isn't true.
You mean
about
descendants?
okay, so
no, they're not descendants. They can't be descendants because they're in a different representation too. I mean, the question is, what is the primary that is not in the completely symmetric representation?
Yes.
There must be something there, right?
Yes.
And, sorry. So there's still primary operators with derivatives, correct?
Yeah.
Okay.
Yeah. Right. Yeah.
Yes.
I mean, there will be also descendants of this thing here, of course, which contain derivatives, and that's absolutely
right.
That's
exactly.
I mean, if you want to
you mean, for example, you can have a box.
Yeah.
There's things where you have box rather than the mu, the nude, or the rho, I mean, because that's also a higher derivative.
Right? I mean, all we're saying here is that there'll be configurations which will have derivatives which are non-homogeneous, where the ground state is not homogeneous.
Right.
This by construction have to correct, as Oleg is saying. Yeah, I mean, just adding boxes to the other rows. This is the way it works. But this can be, can be and will be primaries in general.
So for the descendant operators, what will correspond to?
Well,
for the ones which are not primaries, what would that be then?
You can construct them, for example, adding a quanta of Goldstones. That's the simplest thing to do. Like even in O2, you can do it.
Yes.
So what you can do? So adding what exactly?
Quanta of Goldstones.
No, it's just the n equals 1.
No, you construct them all. I mean, what you can do
is kind of, you can see them. I mean,
yeah, they're written in there. They're exactly the things.
Yeah, you can kind of scale with this L quantum number.
Exactly. And these are spin-full operators. And then you can see from there you can construct other primaries. From there you construct descendants, and there's a very nice thing that shows you that indeed you get the descendants. I mean, there's a skip by 1, and this comes from LL plus 1. All the structure actually works. There's a naturally nice interplay between the modes on the sphere, essentially, and the construction of what is a primary, what cannot be a primary because there's an energy that has a square root of 3, and things like that. So, and for the O2 model, this is more, I think it's relatively well understood, right?
Yes.
Okay, so.